All right. Good afternoon or whatever time of day it is where you are, everyone. Thanks for dialing in today. So today we have friend to radar everywhere, Ed Rivera-Valentin, who is going to talk to us about some of their work investigating the radar scattering properties of ice all across the solar system. So, just a couple of reminders before we start. Unless you're talking, please make sure that you're on mute. Videos can be on, or cameras can be on or off. You're totally up to you. Um, we are going to try and save questions until the end so that Ed doesn't talk for 5 hours as they threatened to do when we weren't recording. But if you have questions while Ed is speaking and you want to make sure you don't forget them, do feel free to put them in the chat. But otherwise, we'll hold space for questions at the end. So with that, I will put myself on mute and hand it over to Ed. And Ed, feel free to share your screen and take it away whenever you're ready.
How's everyone? So folks should be able to hear me and see now my slides.
Yep, all good.
Awesome, thank you. So saludos all. I'm Ed, and so I'm going to be reviewing some work I and hashtag Team Radar from Adesivo have been doing as we've observed Mercury, the icy moons, and also our own moon, and how the information that we're getting back across the solar system can improve how we search specifically for ice on the moon. And as a general caveat for this, so radar observations come in different types of flavors. I'm going to be focusing on specifically ground-based radar observations and synthetic aperture radar observations. So I'm looking at the backscatter component. I am not looking at something like a GPR, ground-based radar, or sorry, a ground-penetrating radar. And I should turn my camera on. Hey, wait a second. That started from the wrong end. Here we go. Okay, so just as a general introduction to that type of radar observations, so back when Adesivo was functional, the way radar at Adesivo would work is we have this large collecting area where we would be able to transmit radar from the Gregorian dome, which hopefully you see my mouse hovering over it. Radar beams would bounce off the dish, go hit something like an asteroid, and then as the light is coming back, we turn the transmitter off and put in the receiver right at the point of the focus and receive for the amount of time that we transmitted light to and from this object. So because radar is an active type of observing mode, it means that we can do ultra precise measurements because we know exactly what we're transmitting. So generally when I give like a radar talk to the public, I say, in astronomy, you go outside, you pull out a telescope and you sit out and you wait for a stray photon of the universe that has traveled the cosmos and the vastness of the void to finally make it through our atmosphere, hit your telescope, go into your eye, and for your brain to translate that photon into something that goes, ooh, shiny. And in radar, we're impatient. So instead of waiting for the universe to send us the light, we are the light. And that gives us a lot of abilities because we can modulate it or just send out a continuous tone. And so generally speaking, you can kind of box the type of measurements that we can make in radar into 4 categories. We can measure distance and velocity really well. So for example, for asteroids, so typically these objects are hundreds of millions of kilometers away from the Earth. And with Adesivo, we were able to measure that distance down to a meter. And in velocity, asteroids are typically moving dozens of kilometers per second, and we can measure that velocity down to centimeters per second. So although this talk is going to be about ice, for folks' awareness, this is the type of precision you want for planetary defense, because if you recently discovered an asteroid and you want to make sure that you can precise the orbit so you can predict if this is going to be a danger to Earth now in a couple of centuries, this is the type of data you want. The next two things that we can measure really well with data is intensity, one, right? Because I know exactly how much light I transmitted. So compare that with how much light I got back. And now I know basically the radar reflectivity of the object. And the last one is polarization. So for at a seawall, we would transmit a circularly polarized light. It would go out into space and it would come back, and we would see both senses. So the opposite circular polarization, the same circular polarization as was transmitted. And so intensity tells you something about the potential roughness of the object, also its dielectric permittivity. The polarization state also tells you primarily stuff about the roughness of the object, and then a bit about the composition as well. And as we go through the talk, I'm going to kind of complicate things and then show you where the caveats come into play as we're interpreting this and why then that matters for prospecting for ice. So as we illuminate an object, our beam goes out, whether it's from Adhesival or mini RF, and it hits an area with topography or it's illuminating the entire sphere. So I'm seeing curvature. And so that changes the incidence angle upon which my light is going and hitting. If the object is super smooth, then all of my power is going to come back at zero incidence, and I'm not going to have much backscatter if I'm at different incidence angles. The rougher something is, the more of that power gets distributed across different incidence angles. And that's what I'm showing you here in this example. Then, typically speaking, although you already see a caveat here, the radar reflectivity at low incidence angles, specifically close to zero, that is related to what is called the Fresnel reflection coefficient, which is related to the dielectric permittivity of the material. So if we have that number, then we know something about the composition. Then we can look at what's typically called the shape parameter, so how much power is being distributed across higher incidence angles to get at an estimate for the roughness of what we're looking at. Now, I mentioned that Adhesival and mini RF and other instruments can receive multiple polarizations. For Adhesival was OC and SC. And in these graphs from a paper by Volatiles 2011, we can see the different aspects of the surface that end up going into producing the overall observed radar backscatter. First thing to know is that when you're looking at the OC, the opposite circular polarization, the dominant process or the dominant physical property is surface scattering, just at about 20 until at 20 degrees, until then volume scattering starts playing a role. But even then, surface scattering is pretty much dominant for a bit and then kind of whooshes on down. Other aspects like subsurface and volume scattering are not dominant when you're looking at this. When we're looking at the same circular polarization, you can notice that volume scattering is the dominant process leading to SE backscatter. At the angles of close to zero, we have almost no effects from surface scattering. That only kind of jumps up after about 10 degrees. And then other processes mesh around. Now, in radar, and especially when we've been talking about trying to find ice, we say, hey, let's look for high CPR numbers, and CPR greater than 1 or something like that. That will tell us where water ice is. So what is CPR? CPR is the ratio of these two numbers, SC and OC. And at the bottom, you can see how CPR might behave with respect to incidence angle. You can see that generally increases. So caveat number one, when we're talking about using the singular metric to try to infer surface properties, is that the context matters. If you're going to be comparing CPR of 0.5 at something of incidence angle from 0 to 10, comparing that to something that was observed at incidence angles 70 to 80, that's a poor comparison. That context matters when you're trying to interpret what CPR is. The other take-home message from this plot, though, is I went through and I was trying to describe the different physical properties that go into producing or dominating the radar backscatter as a function of incidence angle, because if CPR, since CPR is a ratio of these two values, we end up taking, so between 0 and 10, you might have surface scattering dominating in the OC, but between 0 and 10, surface isn't dominating in SC, but volume is. And then as you transition, you see that the each of these properties end up changing as a function of incidence angle differently with respect to OC and SC. And now you're taking the ratio of that, and somehow that's going to be super meaningful. So the caveat there is when you're trying to infer CPR and you're putting these two um, values together when they're being affected by different things at different times, things get a little bit complicated. But generally, we have found that if you take a map of CPR over the moon and we find that high CPR values tend to correlate really well with rocky regions, low CPR values tend to correlate really well with flattish stuff. And we do generally end up seeing high CPRs associated with things that are water ice, like the icy moons of Jupiter. Those are generalities. It's, I would say, important to look into those generalities and better understand those caveats, which is what I'm going to be doing here. The first one is, so water ice and CPR. We keep the general rule of thumb that I just mentioned was that high CPR is a good indicator of water ice. So if we look at Mercury, in this plot, what I'm showing you are the black dots are regions in the North Polar terrain that are not PSRs. And the blue dots are regions that are PSRs, and we know have radar bright deposits in them. A messenger has confirmed that there's likely a volatile signature there. And you see, cool, the CPR is greater than 1, but this mumbled mess is pretty much indistinguishable from each other. So just based on the CPR value, if I had just a CPR map of Mercury, North Pole, it would be very difficult to go, here's water ice and here is no water ice. So CPR, it turns out to not be a robust diagnostic of buried water ice. Instead, there's been some modeling work done by Ann Verkey and Sriram Bidavasu looking at how we can better untangle this. And so going back to that previous slide where I told you SC and OC act differently, perhaps we should untangle them and look at them separately instead of putting them into a single metric. So that's exactly what Ann and Sriram are suggesting. So instead of looking at them in a single metric, you can plot them as SC versus OC in a plot, and you suddenly see that the values for background terrain and PSRs, poof, they separate out into clearly distinguishable classes with little to no overlaying of these values. And so it makes it far easier to be able to identify the radar bright deposits as compared to the background terrain by looking at things separately. In their method, they actually went further than this. What they found is that I found a least squares fit line to SC versus OC, the slope of the line is related to the general roughness of the region. So that's either the abundance of wavelength scale scatterers or the morphology of those scatterers. Instead of appearing nice and spherical, they might be rugged. And then the intercept of the line is related to the dielectric permittivity of the material. So one thing that we've been playing around with that method is amending it a little and saying, well, because you have these relationships between the property of those lines, well, I can now fit, a line to just the radar bright features and then compare the results to a background terrain. And if I ratio everybody, then perhaps since the background terrain might have a lower dielectric or whatever, the relative intercept value might be smaller or higher. The same thing with the slope. So we can start like generating this quad chart where if your intercept is greater than 1, once you ratio those two terrains, then the terrain you're looking at likely has a higher dielectric permittivity than that, let's call it the control terrain. And if the slope it has a ratio less than 1, then the terrain you're looking at might have more and or rougher scatterers. On the other end, if the intercept is lower, then the terrain you're looking at likely has a lower dielectric permittivity. And if the slope ratio is higher than 1, then you're likely looking at a terrain with less and or smoother scatterers. So we start quad charting this, instead of using just a singular metric like CPR, we looked at SCOC and then we broke it down again still into two different measurables and trying to relate terrains with each other. And so that was the result of a talk I gave at LPSC back in 2023, where I validated the technique with data that Sriram and I had taken of Mercury back in 2019. And once that was validated, we said, okay, cool, let's now use mini-RF data on the moon and do this type of quad charting and compare and contrast some known PSRs that may or may not have water ice in them. And we did the comparison with respect. So the control regolith was non-icy regolith that we knew was not a PSR. And we ratioed all of these. So that's what I'm showing you in this plot. And one of the results ends up being, so there's a PSR within Hermite here in yellow, orangey yellow, gold, let's call it gold, where you see my mouse hovering over it. You see that the ratio of it with respect to the intercept and the slope as compared to a nominal terrain is basically 1, right? So that means that section that is a PSR within Hermite is at least indistinguishable from nearby terrain in terms of dielectric permittivity and its general roughness. So perhaps it doesn't have water ice, or perhaps it's buried deeply enough. Then we have these other PSRs that we looked at, Malacan Crater, PSRs within Cabeus, and other sections of Hermite. One thing that we noticed is that the slopes is always, the relative slopes are less than 1, which means that these terrains, these PSRs have either more and or rougher scatterers, wavelength scale scatterers. And the other thing to note is then that the intercepts fall on both parts of the quad chart. So Malacan and Cabeus end up on the higher end of things. So their intercept is suggestive of a terrain with a higher dielectric permittivity. And folks, Hermite is falling on the lower end. So its dielectric permittivity is lower than non-icy regolith. And so to me, that's already suggestive of potential variation in the amount of water ice that might be within these PSRs. But obviously, more craters need to be looked at for the study to be finished. And different radar scattering models should be employed to better untangle what this is saying. But this was back in 2023, and I should finish this paper. But there's a lot of things going on. But for this part of the talk, so throughout the talk, PS by the way, I'm going to be like stopping in the middle and saying, here's a lesson learned from X body for the moon. And so the first lessons learned from Mercury about trying to find ice on the moon is CPR by itself is not a robust diagnostic tool to search for buried water ice on the moon. By itself, you can pair CPR with SC and OC. You can pair CPR with degree of linear polarization. Pick your favorite polarimetric product. But the point here would be that polarimetric analysis, which I already showed, can reveal those subtle differences in scattering behaviors. That will be the stronger tool in order to better identify water ice and then start characterizing its abundance or its state in these PSRs. That's the first lesson learned, I would say, from Mercury. Okay, so now let's go back to Mercury and do a couple of extra steps there. So besides looking at the PSRs as just a whole bunch of radar backscatter points, let's start looking at them in detail. So on this side, you're looking at SC radar backscatter map of the northern PSRs. And I'm pointing out the average radar illumination because this is an average SC radar backscatter map over an entire week of observing runs that we did. And so one of the things that we then wanted to do, and what's published in the 2022 PSJ paper, is let's start looking at each of these PSRs in detail. So I ran a couple of algorithms to try to separate out the radar bright features using unsupervised techniques. That way I'm not picking each place by hand because that's a lot of work and I'm not doing that. And then we also applied different algorithms to try to cluster the amount of the bright radar brightness of these features. And so that's what you see on this map over here, where now after applying a k-means clustering algorithm, we can start looking at the variation of radar backscatter across the PSRs. And so that's colored here, where yellow would then be high SC radar backscatter and the light blues would be low SC radar backscatter. And after you do this, it turns out that this also independently clusters things by CPR. So the yellows are high CPRs and the blues are low CPRs. So after staring at that map for a while, one thing I started to notice is that there's kind of like this general two patterns that the backscatter over the PSRs occupy. The first one is the magenta pattern here that I'm highlighting for craters Tolkien, Chesterton, and Tragvedottir. Those you can see kind of have this clear gradational pattern where you have a central super bright region, those things clustering in yellows, then surrounded by oranges, greens, blues, and very nice gradient. And then you have the yellow, I should have picked another color. But you have Kandinsky and Prokofiev, who kind of present more with a muddled pattern. Like if you stare at that, you can't really readily identify like a central bright feature. You might identify little globbies of brightness, but within for example, within this major part of Prokofiev, it kind of looks like a lit up Christmas tree. You have some yellows and oranges and then some greens, but they're not like really correlated with each other in a spatial way. And so our question then for this project was, all right, so there's interesting heterogeneity across the PSRs. We hypothesized then that that heterogeneity might be a reflection of the differences in terms of ice purity across this. So maybe those central bright regions are just really pure water ice, maybe completely surface exposed, or at least as it might be buried under a very thin regolith layer, but that layer should be less than the radar wavelength, so the radar doesn't really see it, and so it doesn't attenuate the radar much. And then some of the more muddled regions might be a little bit more either impure water ice or ice buried a little bit deeper, so you have some attenuation from the radar before it hits the water ice. So we ran some basic radar scattering models just to test the hypothesis. We grouped those regions that were really radar bright that also had high CPR as one family, and then low CPR, low radar bright, but still within the radar bright features. So I'm not saying this is background terrain. This is still bright stuff inside, just dark stuff inside of bright stuff. That's a better way of saying it. And so what you're looking at here is a reduced chi-squared space for the best fit models that we ran for these two populations. And we found that there is likely a difference in the dielectric permittivity of the materials. So for CPR greater than 1, the dielectric values will range between about 3 and 4.5. And for CPR less than 1, it will be between 4 and 5.3. And then we pass that through a dielectric mixing model where we mix ice and some rock impurity, and we see how much impurities does it take to get those values, and we can start setting limits where the brightest stuff might have a 3% impurities inside of it plus ice, and the darker stuff might have up to 20% impurities plus ice. The caveat here is that these are basic scattering laws that we're fitting. And in these scattering laws that we use often in SAR and ground-based radar observations, they primarily rely on two things, the C, which is the shape parameter. So if you remember back to those early slides, shape parameter just tells you how much of the radar backscatter power is getting distributed out into the higher incidence angles. And then the R naught is that Fresnel reflection coefficient, which is related to the dielectric permittivity of the material. But these are basic laws. Once you're inside of water ice, you have likely coherent backscatter opposition effects occurring, and other secondary effects. And so these approximate those processes, but don't capture completely. But still, we're seeing that there's some evidence that there are likely these differences. The next step that we then took is we started looking at it even more detail. And so for this, you're still seeing k-means clustered brightness, but now instead of my maps that happened in 2019, we're looking at the John Harmon maps, which are from the 90s through the early 2000s. And those he averaged over all of those incidence angles. So you're looking at an averaged map over a bunch of different observing runs over a bunch of incidence angles. So by this is a good way of looking at like the general distribution of the radar bright material within the PSRs, but at least for the stuff I do, because it's averaged out, it no longer has correlation with incidence angle, and so like scattering models are no longer possible with this. But we can start looking at areas that are generally really bright. And so here pulled out these craters. Let me move this to the side so I can speed that better. Chesterton, Trivodot, Tolkien, and Kandinsky. And so by now we had Messenger at Mercury. We have really great topography. We are able to do high resolution thermal models of these regions. And so we started looking at the correlation between the radar brightness and those high resolution temperature models. And what we found is that the really bright stuff, so in these maps, you're seeing the magentas and the purples. That really bright stuff is typically less than about 100 Kelvin, right? So right around here, 110-ish Kelvin or so. And so that's what you'd expect if radar brightness is actually correlated with water ice. And then the dark blue and the black here, those terrains are typically correlated with stuff above 200 Kelvin. And so that's where one wouldn't expect water ice. So that's cool. But there's an interesting addition to the story that we found out here. And that is this intermediate terrain. This class 3, which turns out to be the cyans inside of these places are about half as bright as the brightest stuff, but 3 times brighter than the darkest stuff. And they, although they do occur inside the PSRs, you can also see them kind of occurring outside, and it's might not just be we haven't defined the PSR boundary very well, because we also see them outside of the crater. And so they're occurring potentially in regions that are a little bit warmer, right? At these dots, the error bars, if I remember correctly, these were quantiles, so 25th and 75th percentile. You're seeing that in some of these craters, we're getting really hot when we're seeing cyan. It's not correlated to topography, so it's not incidence angle induced changes either. So the potential hypothesis here is that there might be additional heterogeneity inside of these craters. There's interesting backscatter that, although inside of, for example, Trivodot, all of this would be very, very cold. So if has captured water ice from, e.g., a cometary impact, then there should be water ice all over the place. Why is there this random sea of kind of nothingness in the middle? And then the more muddledy crater Kandinsky over here. So the idea here might be that this might be an indicator of surface processes that have occurred, that have weathered some of the potential buried water ice inside there. These might be regions that are buried a little bit deeper. These might be regions that are transitional terrains where you have buried water ice, but then as you go out, that the depth at which the water ice is stable just drops a little bit lower, but it could still be there. And so or it's actively sublimating away or something else. Point is, there exists a transitional terrain here. And so this transitional terrain, one of my thoughts that I had is, if we're looking for dirty water ice on the moon or much more deeply water ice on the moon, instead of just comparing to all of the radar backscatter from Mercury's PSRs, this might be the better analog for trying to better understand the radar scattering for a type of terrain that might occur on the moon, because we at least know that it's not the magenta. Otherwise, Adasiwa would have seen that ice a long time ago. But maybe it's the cyan. And so we can start looking at these specific terrains and see the scattering properties of it to see if we can better identify metrics to find it on the moon. And so pausing here for the lessons learned, even on Mercury, there's heterogeneity between craters, and there's significant heterogeneity within craters themselves. those heterogeneities are likely manifestations of surface processes that have altered the state of that water ice, how buried it is, how dirty it is. But when we're getting into that nitty gritty detail of let's find what the best analog is for understanding that radar signature of ice that we might be replicated on the moon, we need to get to that additional detail and say, okay, maybe this transitional train is better. But also, as we investigate these PSRs, we can start better constraining the type of processes that have acted over time to actually alter their physical properties, and then take those lessons learned to better understand when we're, for example, modeling the obliquity changes on the moon and different impacts, and then trying to predict where that water ice is. We can then take the lessons learned of the surface processes on Mercury and then translate them over to the moon and inform those modeling efforts to then better approximate where we can or should be searching for water ice on the moon. Okay, so those are the lessons learned from Mercury. So now I want to step one more backwards in time. And let's go to the better ice analog, the icy moons of Jupiter, right? Because like if you're going to be looking for ice, go to the things made of ice and look at its radar properties. So when we first were finding ice with radar on Mercury, there were two properties that were like, oh, these might be ice, and that is ICPR and the radar brightness. Those two things seemed very similar to the radar properties of the icy moons of Jupiter and to the Mars South Polar Layer deposits, which is why we were starting to infer that there might be water ice on Mercury. So let's go back to that source and say, okay, we also have out of sea radar observations of the icy moons of Jupiter. And this example, I'm going to be specifically talking about Ganymede because Ganymede has both light and dark terrain. And so it has semi pretty ice and rather dirty ice. And so that might be a better analog for Mercury's PSRs, which already was identifying evidence that there exists variation in that pure impurities across each crater and within each crater. And so went back to that data and we started looking at, all right, now let's develop a radar scattering model just for Ganymede. And so that's what I'm going to show you here. Let's stop for a second. The black line that you're seeing here is the actual radar backscatter as a function of incidence angle. I just binned it into 5-degree bends and smoothed it over. The gray is encapsulating the 2 sigma data variation across it. And then we employed a composite scattering model, which then takes 2 different scattering laws to approximate that CBOE effect. And you're seeing the 2 sigma prediction limits of that model in purple. Why do I use purple and magenta a lot? Because they're really pretty colors, that's why. So we have the hemispheric radar backscatter for Ganymede. We were able to fit different scattering laws. We found the best fit here. This is following the modeling setup in a paper for Titan by Bonafoy et al. 2022. So as a comparison to make sure that the scattering modeling is working well, we found that the dielectric permittivity then generally across Ganymede would be about 2.9 plus or minus 0.2. And that roughness parameter, which is typically given in a root mean square 30 degrees, that compares really well with what they had already done for Titan. And although, yes, Titan is weird and it's not Ganymede, they're ice balls. So as long as like to a first order, they're looking pretty well, that's already evidence that the modeling is working pretty well. And so you see, yeah, the numbers are making sense. They're within expectations. So now we can have like this baseline. And now let's go to Mercury. And then from Mercury, jump to the moon. So as I mentioned, when we first found ice on Mercury, the thing was, hey, the CPR is high and it's kind of radar bright. So they're similar. So here I'm showing you the CPR in purple is that 2 sigma prediction limit from the model by Ganymede. In cyan, we're looking at 2 sigma prediction limit for those craters on Mercury that were presenting that gradational pattern. And in dark blue, we're looking at those that were muddled because the previous work showed that there were potential differences between those two, So I'm going to separate them out here. So yeah, if you look at something in CPR, these all look the same. Yay. But I've been saying CPR alone might not be really good in terms of a metric. So let's break it down like Anne and Sriram taught us into SC and OC and look for differences. And if you do that, there exist differences. And note also like that I'm restricting the incidence angle range between 80 and 60. So this isn't just an over prediction of the model. 80 and 60 is where the data exists in terms of the incidence angles for the radar backscatter from the PSRs. I'm not showing you less than 60 because the minimum incidence angle over the regions are within this terrain here. So it's not an over prediction of the model. These are just comparing model fits and the actual backscatter that we're seeing over these regions. And we are looking at potential differences between the backscattering of Ganymede as compared to the Mercury muddled looking craters and the Mercury gradation looking craters. Specifically in SC, you see that incidence angles less than about 65 degrees, there starts to exist a nice deviation between those two. For OC, the deviation starts earlier at about 70 degrees. And that deviation is true, at least at that 2 sigma level. And so, all right, now that we looked at things a little bit closer, we're starting to see that there are potential differences. What do those differences mean? One of the potential ideas is that for Mercury, the volatile source may have been a comet that came in, and then those volatiles danced around the surface until got captured in PSRs. We know that cometary volatile is not just water ice, there's other stuff inside there. So that might be a different mixture than an ice ball floating around Jupiter that had the ice forming beyond the ice line in the solar system. And then it also had different processes like the radiation environment of Jupiter affecting the composition on the surface, plus other different processes. So this might be telling us or alluding to those differences. And so a lesson learned then jumping over to the moon is maybe the volatile composition is affecting how the scattering properties or the scattering behavior of the PSRs will look like over the range of observed incidence angles. And so if we can better understand the Mercury radar backscatter in context of what Ganymede is doing, in context of what Europa is doing, we can start better understanding, okay, how do then we translate Mercury back over to the moon? And so, because I really want to make sure there's time for questions, summary of all of the lessons learned for this is one of the things that we've definitely been learning over the past decade or so is that although for a bunch of decades in radar, ground-based and SAR, we've been really relying on CPR, it's not, we shouldn't, only rely on a singular metric. Polarimetric analysis is more robust to better characterize the physical properties of the terrain. And if you're just using CPR, context matters. Those were the first 2 sections of the presentation. The context in terms of the incidence angle matters when you're comparing these values. And then as we moved on through the rest of the presentation, we saw how comparisons to Mercury as well as the icy moons can help bolster how we're interpreting the backscatter from the moon, can help bolster how we're trying to search for ice on the moon and inform on the type of metrics that we should be looking for and the expected behavior of that scattering. So that's not only in terms of the scattering behavior, but as we study Mercury, we can understand the different types of processes that act over time and how they act over time to change the properties of these deposits and to change their scattering properties. And then we use that information to also better inform the type of modeling that we do on the moon. And although I don't have a bullet point here, shameless plug, another great thing would be to actually do this in the laboratory and do this under controlled experiments and look at radar scattering under a controlled situation where we can vary the different types of volatiles, we can vary the grain size on the ice, and use that type of laboratory work to better inform all of this type of modeling that we've been doing. And that's a shameless plug because one of the things I'm doing at APL is developing a radar lab for specifically to inform ground-based radar observations and SAR observations in terms of informing the better scattering laws that we should be using, the effects of all of these different properties in terms of the polarization properties of the backscatter. Uh, we're still in the concept design phase, but we're hopeful that by this time next year, we will be able to have a fully functioning lab and we'll be doing all those cool experiments. And with that, I will say thank you so much for hearing me blab about stuff.
Yay, thanks, Ed. I'm trying to find the applause emoji, but I can't find it. Oh, wait. I found it. Yay. But thank you. That was awesome. All right. So um we have time for questions. And I see we have one in the chat from Ashish who asked if the formation of the craters itself can cause heterogeneity within PSRs. And I'll let Ashish build on that if he wants to.
Yeah, actually, before I respond, Ashish, would you like to add additional stuff?
Hi, Ed. It was a
Hey,
nice talk. Yeah. You showed four craters and the heterogeneity within the PSRs, right? So when I look at the plots, I see that the water or the volatile is almost towards the rim of the craters, and you also mentioned that is somewhere outside the craters also. You find something outside. So will it be directly connected to the formation of the crater itself, that the material is pushed away or no particular? That's what. Yes. My question
I
is
see
clear.
what you're saying. So at least for Mercury, we don't think that the water ice was indigenous to Mercury. We think that it came in from a cometary impact. So, however, the crater formation itself, although it might not impact the distribution, because then the idea here would be that the craters were there and then a comet came in and water ice bounced all over the place. The morphology of the crater itself would affect the not only the temperature environment of it because of differences in topography and where the light is actually is able to make it in from scattered light from a bunch of different sources, but also in terms of the expected porosity, the expected material properties, where water ice can eventually diffuse and become part of that crater. So, although the formation itself may have not told you where the water ice is, the effect of the formation and the topography and potential properties of the regolith in the crater, which are a manifestation partially of the formation event, could tell you something about that indirectly. Yeah.
Okay, thanks.
Yeah. Thank you.
Cool. Yeah, that was a good question and good answer. I guess building on that, like just because that sort of prompted the thought, but are there craters that might be younger than the ice that we can resolve with radar on Mercury?
Say that one more time because I thought you were going to go somewhere and my brain went to that answer and then I didn't hear the
Okay.
rest of it.
Yeah, and then you can go there as well. But I was just wondering, like building on Ashish's observation that or thought that the crater might influence what happens to the ice. But like, are there smaller craters on Mercury that might be younger than the ice deposits that we can resolve with radar?
Younger craters on Mercury that are younger than the formation of the PSRs themselves. So,
Or
because in my
younger than the ice. Yeah.
younger than the ice.
Like, could
So,
there be places where there was ice and then there was an impact? Could we see it with radar?
so if people gave me a higher resolution radar, see, so next time we go back to Mercury, let's please send a radar. There's in Prokofiev, right? In Prokofiev, I can almost convince myself that an impactor came in and extruded water ice from beneath, and because I can see in the topography where the impact is, and then kind of surrounding that region, there was brighter pixels than within. Um, but this is 1.5 kilometer resolution radar. I would before I would say that that is a true detection, I would much rather have much higher resolution radar imagery to super double check that. Actually, where I thought your question was going, so I'm also going to answer that one, is like, is there a source crater or impact for the water ice? And I think there's been several studies looking at that, and right now, like the highest candidate crater, at least the last time I checked the literature, was Hokusai. It has the beautiful ejecta rays going across Mercury. They appear in the global radar images that I have. They're so pretty. And so the idea there would be that it is young enough to have been that cometary impact that then gave all the water.
Awesome. And I see Chris has her hand up.
Yes, hi Ed, thank you for the talk. It was super useful for me. I have a question. So you mentioned that it is important to have like a control environment to better understand the effect of different parameters on the radar signals. I completely agree. I was just wondering if there is like a software that you use or that can be used, and what is the limitation of like software, kind of in the style of like Sizeware for seismic data? What is the limitation of software compared to like the lab that you're building? Like, yeah.
So software as in like the radar scattering models and stuff like that?
Yes. So for example, Sizeware, you can input like the distance from your source, kind of the terrain, the electric properties, and you kind of predict what you will see in a seismometer in the field, right? So for radar, is there an equivalent, or there's just no software that we can use to kind of estimate certain parameters?
Yeah, so there's a fully fledged software package for planetary radar observations. Not really. There are packages, but they come from like the space engineering perspective. So if you want to know what the radar backscatter of a hunk of metal floating around the Earth looks like, those packages will get you down really well. You can manipulate those packages to get you to understand, to get you to predict what the backscatter of a planetary style of environment would be. But they have limitations because there's assumptions. There are non-heterogeneity assumptions made in those type of packages. So for a lot of the type of modeling like that I showed, and the modeling I mentioned that Anna and Shriram do, those are like packages that we each kind of wrote ourselves separately. Anne has this really great package that does like the predicts the radar backscatter, and she can change the morphology of the regolith, the size frequency distribution of the regolith grains, and then also include heterogeneity in the column, in the radar penetration column. The original idea for the lab actually came out when, so Anne was a postdoc at Odyssey while I was there, and she was talking about her models, and we found out that there are some basic tuning forks parameters that she has in those models and certain scattering laws that are used in that are assumptions that haven't been actually validated in lab. So she was like, oh yeah, it would be really cool. Like if we had the validation, if we actually had this number from the lab about how this specific process worked. So the stuff that we do use, there are known limitations on it. And I'm trying to, hopefully by next year, be able to produce data that helps mitigate those challenges and those codes that folks have written.
Perfect, thank you.
Thank you.
All right, what other questions do we have for Ed? All right, while folks are thinking, I'll ask one. So Ed, so you talked about your LPSC abstract where you'd looked at Cabeus and Hermite. Do you have you looked at more craters since then? Do you or do we have the data to sort of look at all the craters in the same way, or are there limitations?
No, we definitely have the data to look at a lot more craters in the same way. Um, in fact, I think at the team meeting for the survey mode node that we're at, Caleb and I were like, would it be cool? So that's I think would make a great follow-on project. I have not looked at more of those craters because so I have ADHD and I got totally sidetracked by a bunch of other projects that became way more shinier than this one. But I should come back and do other craters. Also, if there's like craters of interest besides Cabeus and Hermite and Mountain that folks are like, you should definitely look at this one. That'd be cool to know. Just to start up where to know to start off from.
Yeah, I guess I mean other folks might have other ideas as well, but I guess one of the things I was thinking of was, so early on there was this idea that we see some radar anomalous craters and maybe those are where the ice is, even though later analysis seems to suggest that, that maybe that's just roughness. But it might be interesting to look at those anomalous craters and see if there are differences between those or between those and the non-anomalous ones.
Yeah, so that was actually a topic of Anne and Shram's paper when they first were developing the methodology. So Anne's part of the paper was developing the methods, doing the scattering models, and Shram's addition to that paper was then saying, let's look at these anomalous craters, and they found that there was no major difference that could be attributed to only dielectric changes. The roughness parameters were the more significant aspect of it.
Yeah, I can't believe I forgot that. That must be why it sounded like such a great idea because I admit it. I'll put the link to that paper in the chat. You
Yeah,
can find
it's a
it.
great paper. They did an
Yeah,
awesome
it is.
job.
It is. Temporarily my mind went blank. All right.
Yeah,
What other radar questions do we have for Ed? Yeah, Jason, go ahead.
Yeah, thanks for a great talk, Ed. I wanted to ask if there was a particular reason why the difference between Mercury and Ganymede you were favoring a compositional interpretation versus, say, roughness or some other directionality of the scatterings or something in the modeling that led you to that?
yeah. So because if I was looking at a specific terrain and I was just doing a model for a terrain and a model for maybe one crater on Mercury, then I would say it is ambiguous enough that I'm not going to take a side. But because I was taking the full radar image from Ganymede and taking all population of PSRs from Mercury, where the roughness is kind of going to average out and they might be very similar to each other, but there are still significant differences from the radar backscatter. I start siding with the potential effect of composition, not I start siding with. I'm not going to say I confidently say that it should be composition. I start siding with the compo argument for the bigger difference there. If that answers your question.
Yep, thanks a lot.
Yeah.
And I see Christina has a question in the chat, which I'll read since Christina's mic isn't working. So you mentioned that impurities in ice can affect radar scattering. Is that more sensitive to other volatiles or to dust in the ice, or are they about the same? And Christina also says, thank you for such a cool talk.
So when I was mentioning those impurities, I was specifically talking about like rocky impurities. And so the reason there is ice, you can imagine it to be rather transparent to radar. The penetration depth in radar, the penetration depth in water ice is about 10 meters, for example. In pure regolith, it's about a meter. So there's a huge scale of a difference there. And so like if you can imagine like a radar beam trying to go through ice and suddenly sees a rock can attenuate the power and it eats some of the power up and reflects less going on. And so it affects the coherent backscatter position effect, which means like the radar came in and kind of did a circle and came back out. And so the thing that will impact more that radar backscatter will be impurities who can attenuate the radar wave as it's going through it. Most volatiles don't, I should not say that. Many planetary relevant volatiles do not significantly attenuate the radar, so their effects inside of the matrix might be less than what one would expect if you had something like a piece of rock inside of it. That answers your question.
All right, we have
Awesome.
great. We have time for maybe one more question. And Jason again. Yeah, go ahead.
I'll ask one more then. I'm curious about your lab scenario. Is this going to be a macroscopic kind of sample of ice that you have in mind, you know, on the centimeter or that sort of scale, or is it going to be something much smaller and you're going to basically extrapolate from there?
We are
By
going
the way,
to
it's a
try to.
really cool idea. I'm glad you're doing the lab thing. It's really neat.
Awesome, thank you. So we're going to try to replicate as best as we can real planetary material. So, for example, 2 weeks from now, we're actually doing a proof of concept experiment with a setup that is similar to the one we're envisioning, where like I'm taking a big chunk of meteorite and I put it in front of the radar, and I'm going to vary the incidence angle, and I'm going to see what I get. And I'm also going to measure how much radar went through to get to the dielectric permittivity. So we're looking at big chunks, but we're also looking at, so there's multiple ways of doing these type of measurements. One of them, you kind of put them in a waveguide and then put the material inside there and then see how much wave comes through. That is better for the smaller stuff. So we're adding to the concept, doing that plus the big stuff. That way, for example, I can characterize the dielectric permittivity of like each different material that might be in the composite material separately, and then do the composite material and then test which dielectric mixing model best replicates what I'm seeing in the material, given what I learned about the different, each of the constituents. So we're going to be doing, for that, we'll be doing both, but for like the actual, how much power came back as a function of incidence angle as, and looking at the different polarization, linear, circular, whatnot, that will be on large materials and at temperature. So we're building an RF proof freezer to stick the material inside there and zap it. It's going to be so much fun.
That's great to hear. Thanks.
Yeah.
All right, so we are coming up on the top of the hour, and Dave Blewett says in the chat that yeah, Bourget and all have done some optical frequency analog lab measurements. So yeah, check that out. But yeah, Ed, any parting thoughts before we close out?
Radar is awesome. Right now, we only have Goldstone left in terms of ground-based because we lost out of SeaWorld. So it'd be cool if the community came together and also was advocating for another radar facility, because Goldstone is not meant to be purely planetary. And also let's send radars everywhere. Wouldn't it be great if we had radar at Mercury and like a GPR at the moon and a SAR over at Mars? I'm just saying, an entire fleet of radars would be great.
Yeah, sounds good to me. All right, well, we're right at the top of the hour, so thanks everyone for dialing in, and thanks Ed for a great presentation. And yeah, we will talk to each other again about a month from now. And as soon as the recording's done, I will pass it along to Ricky Guest to put on the Survey Volatiles focus group page. Thanks for joining, everyone.
Bye.
See you later. Bye-bye.